Hello everyone. In this video, we are going to be using our Excel tools in order to help us do confidence intervals with respect to means. Let's take a look at our data. So in this problem, it says O'Shea is out trying to do a study on the number of hours students at his college spend on their phone each week. He randomly selected 69 students and had them report the number of hours on their phone for a week, and the data is recorded below. He decides a good place to start is trying to determine the number of hours spent on the phone each week. And he wants to have a 92.5% confidence level. Okay, so first things first, let's go ahead and grab our data. We can click on our data, highlight across. Let's go ahead and copy that, and let's bring it over to Excel. So I'm just going to drop this into A1. I'm going to do a paste special and text and click OK, and that gets my hours of phone per week right here. Our first question is just kind of a review based on let's look at this real quick, on some vocab. So when we do these, I typically like to do them first, figuring out what is the parameter in the population, then I do the sample and the statistic, and then I do the variable and the data. So the parameter is simple because it's the big group that we're interested in. So we're interested in all students at O'Shea's college. So that's going to be the, not the parameter. This is going to be the population, letter F. The parameter is the truth about all the students at O'Shea's college. So if we look at this, we could say like the mean number of hours spent on the phone for the entire college, that would be our parameter A. If we now go to our sample, that's our small group. So this is going to be the 69 students selected to measure the number of hours spent. So that's going to be our sample, E. And our statistic is the truth about that sample. So that's going to be the mean number of hours on the phone by the 69 students selected. So that will be our statistic D. Now all we're left with is the data, and the data is just the list of those recorded values. So that'll be C. And then the number of hours spent on the phone for a single student is just our variable, and we'll list that as B. I typically like to do it in that order. I think it's the simplest, once again, to start off with your population and your parameter, then do your sample and your statistic, and that is left off with your data and your variable. Okay, so now that we're doing this, we've got to kind of jump into our confidence intervals. So let's kind of do just a quick little review graphically of what our confidence intervals are. So when we take a sample of data like we have here, we know that we can figure out what X bar is, which is just our sample mean. And we don't know what the population mean is. Like, this is why we've gone out and collected data. But what we can say is that if our distribution, if our sample size is large enough, we know that the sampling distribution will be approximately normally distributed. And we can see that if we go to our cheat sheets on page 2, we can see that here, let's zoom in just a little bit, that for our means, that we said that, hey, the sampling distribution of X bar is approximately normal if either the original distribution is normal. I don't know how this data is distributed. I don't know if it's normal, but if the sample size is over or equal to the size of 30, I know that my sampling distribution of X bar is approximately going to be normal. And this is going to be centered on the true mean. But the problem is that I don't have enough time to do a ton of these samples of like size 69 over and over again. So what we're going to do is we're going to do the next best thing that we have, and we're going to center this thing on X bar. And then we're going to perform a couple of different confidence intervals. So the first one that we're going to do is do a two-tailed confidence interval, where we're going to take like 95 or like 92, or we'll take like the middle percentage and say, hey, I'm 92% confident, 95% confident that the true mean is within this range. And then we're going to go through and say, hey, I am 90 whatever percent confident that the true mean is at least a value. So that is a one-tailed. And then we can also do, I'm 95 or 92% confident that the true mean is no more than some value. So we've done these shadings before, we're just doing it a little differently, where now we're going to center this distribution on the sample mean and give ranges of where we think that the true mean actually is. Okay, so let's go ahead and erase that out. And let's look at this first question. So it says, does O'Shea need to worry about the distribution of the individual times spent on the phone? And the answer here is that no, I don't actually have to worry about the original distribution because the sample size is large enough to invoke the central limit theorem, and I know that the sampling distribution is approximately normal. Okay, so let's go down to our next one here. So we know that we're dealing with confidence intervals. Let's do a couple things real quick. So let's state what our variable is. So our variable is going to be like hours on phone. And the data type is, we can say that this is numerical. And it is specifically ratio because it has a true 0. So we know that we're dealing with numerical data. So when we look at our cheat sheet, we can go into this numerical section and we have two options here. We can have one option where it says that I know what the population standard deviation is, sigma, or I know where only the sample standard deviation, S. Now, in reality, most of the time, we don't know what the population standard deviation is. We only know what the sample standard deviation is. If that's the case, we need to go and actually calculate our sample standard deviation. We should double check here in our scenario. In our scenario, the only information that it gives us is a sample size and the confidence level. Let's actually go ahead and start off with typing those few things down. We know that the confidence level here is equal to 0.9275. And it's because they say that that's what our confidence level is. Besides that, it doesn't give us, it gives us a sample size, but it doesn't give us a population standard deviation. So we know that we're going to be in this sample standard deviation slot. So I got my confidence level. Let's go ahead and set what alpha is, because alpha is super easy. It is just going to be 1 minus this confidence level. The next thing that we can look at is it asks for the sample size, an n. And there's a couple ways that we can do it. One, we could just type it in because it told us that the answer was 69, or check out what we can do. We can use our formula, count A. I'm going to click on the first observation that I have, do Control-Shift down, and end with the parentheses, and that will give us, oops, I don't know why it didn't grab that first one. Let's do it again. Put on the first one, and we'll do Control-Shift down, and end with the parentheses. There we go. I got everything highlighted this time. And for me, it's A2 through A70. Your values may be different, and that's great. Everybody's numbers are different on this one. But what we can all do is we're going to copy this range because we're going to use this range a few other times to calculate out some of our summary statistics. So it says that my sample size is 69. The next thing down that it asked for is degrees of freedom. Now, degrees of freedom are important because if we do not know what the population standard deviation is, we have to actually use a different type of a normal distribution. So our original normal distribution, if this is a z distribution, we only get to use the z distribution if we know sigma. And the thing is I just said that we don't know what sigma is. So what we are going to be using is actually what's called a t-distribution. Now, for all intents and purposes, a t-distribution looks very similar to a z-distribution. The only thing is that our t-distribution is just a little bit more conservative. So again, if the blue one, well, let's say this blue one is the z-distribution. Let me get another color. And let's say that this red is going to be our t-distribution. The t-distribution is just a little bit wider and flatter than the z-distribution. Now, as the sample size increases, this distribution gets closer and closer to approximating the z-distribution. For what I need you to know is what are the variables that we need in order to use this new t-distribution, and there's actually only one other that we need to know. It needs to know what's called the degrees of freedom. The degrees of freedom are really easy to calculate. All it is it's the sample size minus 1. And now we have our degrees of freedom. Perfect. The next thing that it asks us to grab is x bar, which is our sample mean. So I'll just hit x bar. And we know already how to find this sample statistic from using our equations. We could just type in average. And I'm going to paste in my range again, A2 to A70, and I'll hit enter. And that gives me my sample mean there of 13.942. Let's keep on going. We know how to get the sample standard deviation. It's S equals STDEV dot S for our sample standard deviation. And we'll plug in our data there. And now we want to calculate the standard error. And over here, it gives us how we calculate out our standard error. It's S divided by the square root of N. And if you don't remember how to calculate X bar or S, I give those equations right next to them as well. So our standard error is just equal to our sample standard deviation divided by the square root of our sample size. Now, just be careful. Be sure that you click on the sample size, not the degrees of freedom. And we've got our standard error. The next thing that we need is our two-tailed t-critical value. And we need this t-critical value. Let me show you. So what the t-critical value is, let's get this drawn up once again. So let's say this is our t-distribution, and it's centered on x bar. And we want to know where is the middle, like this, 92 or 0.9275. We want to know where this area is for above and below. What the t-critical is how far from the mean, the number of standard errors that we go. T-critical is interpreted just the same as like our z-critical, or the number of standard errors away from the mean. In order to calculate this, we're going to use our t dot inverse dot two-tailed. So we have a nice formula that will calculate this thing out for us very simply. So let's go ahead and do it. Inside of here, so I'm going to do t two-tail, and that's just going to be equal to t dot inverse dot two-tail, and then it asks for a probability. What probability it's asking for is our alpha level, or the percent of the time that we're going to miss capturing our true mean. So let's grab our alpha level, and then it asks for the degrees of freedom. So we can just click on the degrees of freedom and hit enter, and we get a t of two tails. And that should make sense to us. Notice how it's about two standard errors. Remember, when we use our empirical rules, plus or minus two standard errors is roughly 95% of the area under the curve. So that checks out really well for what we're looking for. We notice here there's also a t for a one-tail. We'll come back to this one when we need to calculate a one-tailed confidence interval. The last one that we have here is the margin of error, and we only need the margin of error when we are doing a two-tailed confidence interval. And it's very simple. It's just the two-tailed t-value times the standard error. So we'll just hit equals two-tails times the standard error, and we'll hit enter. Okay, now that we've got all of those, let's go back to our problem. Let's start actually answering a few things. So the first question it asks is, what is the best point estimate of the average time on the phone? And that is our sample mean. Our sample mean is our best point estimate. Let me just label that out. Best point estimate. It's our single best guess of what our true mean is. Now we know it's wrong, and that's why we're going to create a confidence interval, because we're saying like, we know our best estimate is wrong, so let's give a range of where we think this true mean actually is. So we're going to provide a confidence interval for the average phone time between two times. And if we look at this, this is asking for a two-tail because it doesn't give us any directionality. So two-tailed is easy. Check this out. It's literally our x bar minus the margin of error and x bar plus the margin of error. It's like, okay, so if we do a two-tail confidence interval, we can say that the lower is equal to, we can say our x bar minus the margin of error and hit enter. And then let's do the upper. And that's going to be equal to x bar plus the margin of error. And so we think that the upper and lower values are somewhere between like 13.27 and 14.61, as we think that the true mean is in between those 2 points. So this confidence interval is a two-tailed. Let me just give you a quick graphic of why this is a two-tailed. So when we draw out our little range and we put our x bar right here in the middle, and we say we want to know the 92.75% confidence interval, it's two-tailed because we could possibly have overestimated or underestimated by these two regions. There are two tails where we could possibly be wrong. All right, let's erase this out. And let's work on to our next question. So it says, select an appropriate conclusion about our confidence interval. All right, so confidence intervals, there are some good ways to write these out. And if we scroll to the bottom of our cheat sheet, notice here, it says for two tails, typically this is how we're supposed to write them. We are blank, the confidence level percent confident that the true population parameter for state who we're talking about is somewhere between the lower and upper units. So this is good for both when we're dealing with means or proportions, but let's plug it in right here. So it says we are 92.75% confident that the true, what are we looking at? The true mean hours on the phone for students at O'Shea's College is somewhere between 13.27 and 14.61 hours. So we click on the right one, and that is what we are looking for. Now, there's a few other things in here. It's like, okay, what are the things that are wrong in these other ones? Well, one says that we are like saying that we are confident about the sample mean. The problem is like, I know what the sample mean is. I'm trying to make a statement about the population value. So that's why I want to say I'm 95% confident that the true mean, or sometime we'll say, or it's like 92.75% confident that the true mean, or that the population mean. The other one says that these are saying chance. And the problem with when we say chance is that we are giving a amount of chance or probability to the population value, and the population value is fixed. It doesn't move. It's not changing. What is kind of fluctuating is each time when we run these samples, we get slightly different nets, or these slightly different confidence intervals when we are running them. Anyhow, if you need some help on how to do those statements are right here at the bottom. Okay, I'm going to scroll back up to our little equations here. Okay, the next one down, it says, suppose O'Shea wanted a confidence interval to claim that the average phone time was at least some value. Let's draw out another picture. Remember, pictures are going to really help us right now. So if we want to say, hey, we're 92.75% confident that the average phone time is at least some value, we're giving a minimum value and saying that it could be bigger. So when we say it can be bigger, it can go all the way to infinity. And this is called the lower tail. Notice where our error region is. Our error region is this lower tail. That's why we have a lower tail over here. Okay, let's erase this out again. And let's do a one-tail confidence interval. We'll do one-tail confidence interval, and we'll do this as a lower tail. Okay, so now we need a lower cutoff and an upper cutoff. Let's see what our confidence interval cheat sheet has to say. So the first thing that we need is we're going to also need to grab a one-tailed t-critical value. So on this one, let's go ahead and we're just going to move this margin of error value down just a little bit. I'll drop this guy down. And I'm going to do a t underscore one tail. We're just going to use this equation right here. So it's just t dot inverse 1 minus alpha degrees of freedom. Here we go. T dot inverse, the probability 1 minus our alpha, comma, degrees of freedom. Click on that alpha. And we have a t value right there. Let's see how we can plug it in to grab our lower bound. All we have to do here is we say equals our x bar minus the one-tailed t value times the standard error. That gives us a lower value of like 13.399. And the upper value is all the way towards infinity because we only have a single tail here. So let's check our answers here. 13.399 and to infinity, because one of these stretch to infinity, we know that this is going to be one-tailed. And we're going to now write a conclusion here. So of our conclusions, we say that there is, let's scroll down and look at our possible options that we have here. So it says we are 92.75% confident that the true hours on the phone, over here, remember, hours on the phone for students at O'Shea's College is greater than this 13.399. Okay, and here we oftentimes, when you talk about it in sentences and stuff, or where we're actually trying to describe it, we round them to be a reasonable number of decimal places. Okay, this next one, it says, suppose O'Shea wanted a confidence interval to claim that the average phone time was no more than some value. Okay, well, if we want no more than some value, let's draw out a little picture again. Oops, let me click over here, draw out our picture. If we want to say no more than some value, we're going to give a critical upper value and say that we can be anywhere lower than that value. And our area where we could possibly have missed the true mean is in that upper tail. So that's a one tail confidence interval with an upper tail. So let's do one tail confidence interval with an upper tail. So on this one, the lower extends towards negative infinity, and I just use two lowercase o's to indicate that. And the upper is actually quite simple. Let's scroll back up to again, this is our numerical one where we only know the sample standard deviation. And we're going to do an upper one. We'll go from negative infinity, and then here it's just going to be x bar plus the one-tailed t-score times the standard error. And that gives us 14.48. And if we look at those, we have done those correctly again. And is this a one-tailed or two-tailed? This is, again, just a one-tailed interval. And if we look at this one, we're going to say that, hey, we are 92.75% confident that the true mean is at O'Shea's College is no more than this 14.48. So that is how we use our Excel tools and some of our graphics, just drawing a simple distribution to kind of see what we're going to do. Now, I really like how we have organized this so that all we have to do is we identify which of these options for confidence intervals that we're going to do. Once you do it, you go down and identify all of your key variables, and then you have to just identify, are we doing a two-tailed or a one-tailed confidence interval? And all of those equations are very simple as long as you go through and you gather every single key variable. I hope that helps you out, and good luck on doing confidence intervals for your means.